everyone for the afternoon session of today. So we'll start with 45 minutes of more quantum groups with Mike Brannan.
Thank you. All right. Well, thank you very much to the organizers and the Newton Institute for the invitation to come here and lecture on this topic. So I'm going to continue on from where Mateusz left off. And I just thought I'd jot down a few of the main points from last lecture, which was the definition of a compact quantum group. Okay, so I didn't write all of the details down, but a compact quantum group, remember, is given by this pair of objects. C of G is a unital C-star algebra, possibly non-commutative. Okay, and together with that is a unital star homomorphism delta, which goes from C of G into the minimal tensor product of C of G with itself, which is co-associative, okay, which is this condition, which is kind of looks like associativity of a map, but written in the opposite direction. All right, and this is sort of to mimic the fact that if we think of C of G as really functions on some sort of fictitious or virtual space, delta should be somehow encoding some sort of multiplication law on that space. Okay, and then there are these cancellation rules, which I didn't write down, but there are some density conditions involving the coproduct. Okay, we will, I'll maybe write them down again later on when I need them, but for now, we'll just leave it at that. So that's the definition of a compact quantum group. And then last couple lectures, we saw a bunch of examples, and they were all matrix compact quantum groups. And somehow these are the ones that you encounter in nature most frequently. Just as in classical theory of compact groups, most of the examples one encounters and does analysis on are matrix groups. Okay, so the class of matrix compact quantum groups is a subclass of the general compact quantum groups, and their axioms are written in a slightly different way. There's a square matrix, an n by n square matrix of generators, Uij, okay, such that our C-star algebra of our compact quantum group is generated by it. And the conditions we require are that when I place all those Uij's into a square matrix, I call that matrix U. I want that matrix to be unitary. It's not actually necessary that I ask that this matrix be unitary. I could just ask that it be invertible. We'll see today, when I talk about representation theory, that that assumption of unitarity of U is actually not strictly necessary. I just need it to be invertible. The other thing I need is that the so-called contragradient matrix, UC, which is basically I take U and put adjoints everywhere, okay, then I want that to also be invertible. Okay, so those are the basic relations I require, and then there could be other relations, as we saw in all the examples, in addition to those, right? So when we talked about Sn plus, there were other relations which made the entries projections, for instance. All right, and then for compact matrix quantum groups, the co-multiplication is defined on the generating set by this form. And it's kind of mimicking how matrices should be multiplied if viewed dually through the lens of a function algebra. Okay, there was a question at the back. Yep.
Can you get a 2 infinity factor from the GNS representation of the higher state?
Can I get a 2 infinity factor? Ugh, I don't know. I'm not sure. Yeah. You can get lots of type 3 factors, but 2 infinity, probably. It's probably something we can do. Yeah. Okay, it's true. And then stated towards the end last time was a very nice theorem which generalized the existence of Haar measure, Haar probability measure on compact groups up to the framework of compact quantum groups. Okay, so translation invariance on the left and right correspond to these two things being equal, and also equal to just applying the functional without actually doing the translation. Okay, so you might ask, okay, what's the formula for the Haar measure for a compact quantum group? And in general, we don't have nice formulas. So in the tutorial tomorrow, one option would be to discuss for SUQ2 a concrete formula for the Haar state on SUQ2. Another thing in the tutorial we might talk about is like, why is it sufficient to, in let's say the examples we look at, only identify or define the co-multiplication by the generating set. Okay, so we'll do some sort of concrete calculations there. But yeah, so the problem of actually finding formula for the Haar state is, I mean, we should expect it to be hard, right? If you just have an actual compact group like UN, we don't have closed formulas for integrating functions against the Haar measure, right? It's even a bit of a disaster if you're integrating monomial functions in the coordinates, right? This is essentially the essence of doing matrix integrals in mathematical physics, right? So we have certain asymptotics and some sort of combinatorial interpretations through Schur-Weil duality, all based on representation theory. Which kind of brings us to the topic of the next couple lectures, which is representation theory of compact quantum groups. So for example, if you think about a function on the circle, right? That's a function on a compact group. And if I wanted to integrate it, if I wanted to know what its integral is, I would be able to do it if I knew its Fourier decomposition. In fact, if I knew the 0th Fourier coefficient, then I know the integral of my function, right? And this sort of says that you know, the Fourier decomposition of a function is somehow very much intimately related to understanding the Haar measure, and vice versa. If I know somehow the Haar measure very well, I maybe understand the representation theory very well. Okay, so that's sort of the thing we want to do now. So in Mateusz's next two lectures, he will talk about the Fourier transform and duality between compact and discrete quantum groups. And this is really built on representation theory. Okay, so just like for compact groups, representation theory, finite dimensional representations are extremely important and essentially can encode everything you want to know about a group. Okay, and this is going to be the same for compact quantum groups. All right, so what I want to talk about now is the notion of a representation of a compact quantum group. And the sort of intuition you should take from this is that if you look at a compact matrix quantum group, right, this is supposed to be a non-commutative analog of a matrix group, right? And a matrix group is a group which is given by a representation of that group in an ambient space of matrices. Okay, so when I want to talk about representations of compact quantum groups, there should be something like these sorts of formulas going on when I talk about representations. Okay, so that's what we're going to do. We're going to model the idea of a representation on that. So definition. All right, so yeah, for this talk, G is going to be a compact quantum group, CQG, which means there's a C of G and a delta with all of the extra stuff. Okay, so I'm going to look at finite dimensional representation. So H is going to be a finite dimensional vector space, but we can throw an inner product on. It'll be a complex vector space, so we can always imagine that it's been endowed with a Hilbert space structure. So a finite dimensional Hilbert space. Okay, so this is of, let's say, dimension D. All right, what I want to do is I want to consider a finite dimensional representation, or let me just say a representation of G on H is a matrix U, which I'm going to write, well, when I write things as matrices, you always have to be aware that you're really fixing a basis of H, or let's say an orthonormal basis of H, with respect to which you write a matrix, right? Because then you really have coordinates, so you're fixing a basis. But let's just ignore that little thing for now. I'm going to think of this as a matrix. And this is, a matrix in Mn of C of G, which is, of course, the same as Mn tensor C of G, which is also B of H tensor C of G. So these are all the same thing as algebras, as C-star algebras. But again, when I write Uij, I'm sort of implicitly fixing a basis through which I identify B of H with Mn of C. So I have an element in this tensor product, and I want to define a representation. So the conditions I'm going to ask are two things. One, U is invertible. And two, that the co-multiplication, when restricted to the entries of U, behaves exactly like it did for the complex matrix quantum groups. Like that. Okay? So this is the definition of a representation of a compact quantum group on a finite dimensional vector space H. Okay? Maybe the first thing to think about is like why is this the right definition? And the reason is, if you think about G, an actual compact group, right? Then B of H tensor C of G. Well, we can naturally identify this essentially matrix amplification of C of G with the space of continuous functions from G into B of H. Right? And the way you do that is, of course, you just think about U, which is going to be this matrix here. The function from G into the matrix with entries Uij of G. Okay. All right. So an object of this form is modeling a function from G into the transformations of H. Okay. So a function from G into matrices. Okay, that's the first thing representation ought to be, but it's more than that. It's a map into the invertible matrices, right? So we want it to be a group homomorphism after all. And being invertible in this tensor product is the same as being pointwise invertible, which is what a representation is. So that's where this condition is coming from, okay? And then finally, so then the image of G, this will always be an invertible matrix. And the last thing is we want it to be a multiplicative map, okay? So U of GH should be equal to U of G times U of H, right? For all G and H in G. All right, and if you spell this formula out in terms of what co-multiplication is, well, this is exactly the same as saying the identity tensor delta of U, now viewed as a two-variable function, right? That's what U of GH is. All right, and on the right-hand side, we want it to be U of G times U of H, which is a product of matrices, right? It's the matrix with entries sum over K, Uik of G, Ukj of H, okay? Which is exactly the matrix whose entries are given by sum from K equals 1 to N, Uik tensor Ukj. This matrix function evaluated on the pair of points GH. So a map from G into invertible matrices which satisfies multiplicativity exactly corresponds to this condition on the entries of this matrix. Okay, so that's where this is coming from. So you'll see the similarity with the definition of a compact matrix quantum group. Okay, there we're saying that there is a representation of G with an extra condition, namely UC, which is not included in the definition over there, is invertible. That will turn out to actually be automatically true for general representations. I don't need to assume that. And the additional thing with the compact matrix quantum group is I have this one representation which is somehow generating everything, okay? And when we say generating, what do we mean? Well, we'll learn about what that means in the language of representation theory. Well, we take tensor products, possibly adjoints, and stuff like that. Okay, so that's the idea. A quick remark here, which is, again, when I write things as matrices, I'm fixing a basis implicitly. This definition of a representation is basis independent, which is an exercise one can do. Okay. Just choose a different basis and there will be a resulting change in the matrix U, and you can check that the same conditions are satisfied. There's another way to see that this is basis independent, which is writing the definition of a representation using something called leg numbering notation, which might be useful for probably the quantum information lectures and also certainly further lectures in this quantum groups course. So I want to maybe just pause for a second and talk about leg numbering notation. So as I defined it here, a representation is really an element of this tensor product B of H tensor C of G. So suppose I have an operator X in B of H tensor C of G. Okay, and okay, H is finite dimensional, so without loss of generality, by expanding things as sums of elementary tensors, let's assume X is a very simple operator. It's a elementary tensor, okay? So it's something in B of H tensor something in C of G, okay? What I want to do is I want to sort of promote this operator to something on a larger tensor product, okay? So I'm going to define, for example, x12 to be, what I'm going to do is I'm going to define it to be an operator on B of H tensor C of G, okay? And what I'm going to do is I want to think of X acting on this larger tensor product as it does in its ordinary way on the first two legs, and then trivially, like by the identity operator on the third leg. Okay, so x12, when I say 1, 2 here, I mean I'm viewing X as sort of locally acting on the 1, 2 leg, and then as the identity there. So this kind of thing you see all the time when you're writing down quantum circuits, for example. And it's the same sort of notation. So what this is x12, if for this operator would just be A tensor B tensor 1. Okay, and similarly, I could do, for example, x13, right, which is going to live as an operator in this tensor product here. And x13 will be, what I want to do is I want to act by X on the first and third leg, and as the identity on the middle leg. And so this is going to be, A tensor, the identity tensor. Okay. So this is leg numbering notation, and you can imagine, you know, how you can do other versions of this. For example, I could have done B of H tensor B of H tensor C of G, and done leg numberings for X there by doing the obvious thing. And we'll see that variant of it momentarily when we talk about tensor products of representations. So maybe another little calculation that one can do, and we can talk about it in the tutorial on tomorrow or Friday, would be U in B of H tensor C of G invertible. So an invertible element of this algebra is a representation. If and only if. Okay. Well, we have this condition and we have this matrix. The co-multiplication condition is exactly identity tensor delta of U is U 1, 2, U 1, 3. So here X is now U, all right? And so U 1, 2, U 1, 3 means I take U and I think of it as acting on the first two legs of, and of course, where is this thing living? This is, of course, living in B of H tensor C of G, tensor C of G. So I act here by U for this first term, and then I act on here and here by U for the second term. And if you write U in terms of matrix entries, that equation is exactly this condition here. Okay? So you see what's happening, really. We're doing the multiplication in B of H, but co-multiplication on this sort of.
Can you also talk about unitary representation?
Yes, good. Yeah, that's a good question. So we say that U is unitary if it's unitary. Okay. So a unitary representation is just, the obvious notion. And actually, one of the things I want to sort of explain is that just like for ordinary compact groups, we can always take a bounded invertible representation, right, something like this, and average it into a unitary one, okay? And that new representation, which is unitary, will be equivalent to the original one in the sense of equivalence of representations. So most of the time, we just only need to think about unitary representations. Okay, good. So, but before we get there, maybe we can just start thinking about some examples. And off the bat, it's kind of hard to come up with interesting ones. So for any compact quantum group, we have the trivial representation. Okay, so the trivial representation is an action or a representation on the one-dimensional Hilbert space. Okay, and it's given by taking U to be just the unit of C of G. Okay, and you can check all the conditions are satisfied. Okay, so this is a representation on the Hilbert space given by C. Okay. If I have a compact matrix quantum group, so if G is a compact matrix quantum group, then the sort of the generating matrix, so the generating U, that's a representation, and we basically model our definition on it. Okay, this is usually called the fundamental representation. Of G. Okay. All right. So that's okay. So in all of our definitions of Sn plus, On plus, Un plus, quantum automorphism group of a graph that we saw yesterday, they were given by basically specifying a fundamental representation of the compact quantum group, right? And as is in the case when you start with a matrix group, how do you now generate more than just the trivial and the sort of fundamental one? Well, you sort of just start doing operations with representations, right? So there's a natural notion. So if I want to build more representations, I can talk about direct sums. Okay, so if U, let's say in B of H, U tensor C of G, and V in B of H, V tensor C of G. So I'll decorate my spaces with U and V to indicate where the representation is. Okay, these are representations. Well, I can combine them into one by adding them in a direct sum sense. So U direct sum V is, you know, think of it really as a matrix with a block diagonal form where I put U up here and V down here, and this is now going to be a representation on HU direct sum HV tensor CFG. Right? So the direct sum we can generalize in this setting in an obvious way. We can also talk about tensor products. Right, so tensor products of two representations, I'll write as U tensor V. Okay, this should be, where should it live? Well, if you think about ordinary representations, I take two and I tensor them. I am acting on the tensor product of the two carrier spaces of the representation. So this should be somewhere in V of HU tensor HV tensor CFG. Should be an object here. And this is, of course, just the tensor product V of HU tensor V of HV tensor CFG. Okay. And what is it? Well, again, if you think about how you define the tensor product, what you do is you take U of G and V of G, and you take the tensor product of those two maps. Okay? Not U of G and U of H, where G and H are different, but you ask that G and H be the same. So it's like a diagonal type thing. And when you take G and H and make them equal, this is like multiplying functions in C of G. Okay? So the right thing, if you do it in terms of leg numbering notation, is it is U 1, 3 times V 2, 3. Okay? So now it's a little bit different than this thing you see with leg numbering. So you now have U 1, 3, 2, 3. So this is in B of HU tensor B of HV tensor C of G. So it makes sense to talk about U acting on here and trivially in the middle, right? And V acting trivially on HU and then non-trivially in its usual way on the last two things. Okay? So we can make sense of this. And if I write it in terms of matrix elements, U tensor V, okay? So if U, let's say U looks like this and V is something like VKL, matrix like this, then U tensor V, what should be the doubly indexed entry of this? This would be, so you should think of this as like a map on the tensor product, so it should be IK comma JL index, right? So U tensor V IK comma JL will be exactly Uij VKL. Okay, so I could equivalently, without leg numbering, just define the tensor product in terms of a basis this way. So again, if you think about ordinary representations of groups, this is exactly what you do, right? You take coefficients of your representation and you just pointwise multiply them, and that gives you coefficients of the tensor product representation. That's exactly what's happening here. Okay.
So when you use letters, is there an also like
Yes, yeah. So that's also a a possible place of confusion. Yeah. So when I have arbitrary letters here, this is not So 1, 3 is I'm somehow interpreting it differently. Perhaps I could have put the leg numbering on the superscript, and that would have been better. But I'm too far gone now, so.
So I'm still confused. So do you want for every group element the original group to have like a specific representation of the group, and what would it mean to be faithful?
Yeah. So right. So what does it mean to be faithful in this sense? So being faithful is actually exactly this kind of thing you see in this definition of a compact matrix quantum group. So a faithful representation of a compact group means I have one representation as a matrix group, right, as matrices. And this should be faithful. So what does that mean? That means that if I look at the coordinate functions, those should generate my algebra function C of G. So that's what a faithful representation would be in this sense. So the coordinates of a representation generate the entire C star algebra, let's say as a star algebra. That would mean this is a faithful representation.
Use the bottom group then to create representations of group?
That's sort of, yeah, I mean, I guess I don't have a clear answer to that question. We can talk about it during the break if we want. Yeah.
Maybe a question about this tensor product.
Yep.
In the direct sum, you wrote U plus V basically in this log form, and
Yeah.
it's like the direct sum of U and V.
Yeah.
And I'm also the tensor product thing of U is U tensor V as being just the tensor product of their matrices.
It's not a tensor product of their matrices, even in the ordinary case of a group representation, right? The tensor, well, yeah, I mean, yes, it is, but you're making it act at you're applying the same element to the tensor product, right? So if you think of U tensor V, right, this is going to be a function of two variables, because it'll be a function on G cross G, but then you're asking that I evaluate that tensor at the same pair of points. Right? So the tensor product is like a diagonal action in a sense of the product group. So tensor products are those. And again, when you think about a matrix group, how do I construct all of the representations, for example, of the orthogonal group? Right? Well, what I do is I take tensor products of the one representation I know that's not trivial, and then I find all the irreducibles by decomposing that tensor product into direct sums. So I want to look at sub-representations. So number 5 on this list should be sub-representation. So I have a representation with sub-representation. And so what does it mean to be a sub-representation? Well, to think about those, it makes sense to maybe first say a little bit about morphisms or intertwiners between representations. Let me just say a little bit about that. So examples will be extended momentarily, but we want to talk about morphisms. Okay. So again, U and V as above. And maybe an important thing to note is that the, well, okay, I was going to say something about if I tensor the trivial representation with any representation, I'm not really doing anything up to some sort of identification. Okay. But that's sort of something we kind of expect to happen. Anyway, so if I have two representations, U and V, as above here, I can define more of UV. So the morphisms from U to V, these are, as you would define it for an ordinary group representations, these are linear maps from HU to HV, such that what happens? Well, they intertwine the representations. So I have U and I have V, okay? And so I can apply T to the left side of U because the domains match, right? This is in V of HU, tensor C of G, and T acts on H, so I can make sense of this composition. What I ask is that this is the same as applying T first and then applying, okay? And again, if you think about this classically, when you define intertwiners, it's usually a pointwise condition, right? We say U of GT is equal to V of GT. Oh, sorry, yeah, TU of G is equal to V of GT. Right? That's what it means. But we don't have points anymore, so we can only write these relations, as relations happening at the level of C of G. Okay? I'm going to be slightly abusive of notation. Mateusz kind of did this in his lecture as well. I'm going to write this just as TU equals VT. Okay, where we really, if you just think of T as a matrix and U as a matrix, you would multiply them like you multiply ordinary matrices. But if you want to be pedantic, it's really this sort of composition in the tensor. Okay. So I'm going to just formally write it this way. So this is the space of intertwiners between two representations. And these spaces have a lot of structure, right? So right, these are linear spaces. So morphisms from U to V. These are linear spaces. You can compose morphisms. So if S is a morphism from U to V, and T is a morphism from, let's say, V to W, then TS is a morphism from U to W. Right? So I go from U to V, and then I apply T. And this relation, you just check the works. Okay? So I can take appropriate products of morphisms, as long as they have the right domains and ranges. What else is true? Let's see, I had a list of things I wanted to mention to make sure I don't forget any. Good. Yeah, so if U and V are the same, so I'm going to look at morphisms from U to U, okay? And I'm going to call this endomorphisms of U. Okay, this is an algebra because of this condition. And it's actually a unidal algebra. Okay? And actually, if U and V are unitary representations, you get something better. A morphism from U to V, I can take now the adjoint, T star, and this will be a morphism from V to U. Okay? So being unitary allows you to actually get that morphisms are closed in the sense of adjoint in the obvious way. In particular, the endomorphism algebra of a single element representation here is going to be a C-star algebra. Okay? So in particular, the endomorphism algebra of U is a finite dimensional C-star algebra. Right? And it's, of course, sitting inside of the bounded, or the, operator sitting. So the finite dimensional C-star algebra. All right. Good. So in this sort of generalized setting of finite dimensional representations, how can we talk about irreducibility? Well, we can just borrow, for instance, the definition that sort of comes from Schur's lemma, or thinking about intertwiners. So we're going to say that a representation is irreducible if its endomorphism algebra is as small as possible, right? So this endomorphism algebra will always contain the identity operator, obviously, because, right, identity U equals U identity. Okay, so we'll say that U is irreducible if the endomorphisms of U are as small as possible. Okay. So U is irreducible representation. And what we'll see is you can, in a sense, decompose every representation into a direct sum of irreducibles. Okay. Subrepresentation. There's some things to check when you talk about subrepresentations, and I'll sort of skip those details, but if I take a project or an idempotent, P equals P squared, in the endomorphism algebra of U. Then I can define V to be P tensor 1 U P tensor 1, which I identify now as an operator acting on pH. Tensor C. No, I don't. If it's not unitary, I don't need this. So if I have an idempotent endomorphism, then I can naturally interpret this thing as an invertible element on this compressed space, which satisfies all my conditions, okay? And this is sort of the prototypical example of a subrepresentation. Okay, so a subrepresentation is really a compression by an idempotent endomorphism. Okay. So in the last, yeah, 3 minutes left. Yeah, maybe I'll just, okay, I'm going to end maybe just by stating Schur's lemma in this context, and it's the same. So let U and V be irreducible representations. Okay, then oh, actually, no, I should talk about equivalence of representations first. So I forgot to mention. So we say that U and V are equivalent representations. Okay, we say U and V are equivalent representations if there exists an invertible T, a morphism from U to V. Okay. So it's the same definition you have from ordinary representation theory, right? An invertible intertwiner means these two things are equivalent. Okay. Another way to say it is if T is invertible, I can write U as T inverse VT. Okay. So U is similar to V by the similarity T. That's the way you should think about it. If U and V are unitary representations, well, what do you say there? They're unitarily equivalent if I can find a unitary intertwiner between them, okay? All right, in the last minute, maybe I'll just write down what Schur's lemma is. So if you have two irreducible representations, the intertwiners between U and V are 0 if U is not equivalent to V. And well, I want to say dimension 1 if U is equivalent to V, and this is the notation. Okay, so the same Schur's lemma holds, and yeah. So roughly, the idea here is right. So if I have a non-zero intertwiner between U and V, okay, I can look at the kernel of that intertwiner, and that will be a subrepresentation of U. And the range will define a subrepresentation by looking at the associated idempotent of V, okay? And, well, morally speaking, again, when you think about subrepresentations being irreducible, although not explicitly phrased in this way, being irreducible means there's no non-trivial subrepresentations of U or V, okay? So, in other words, in the case of this being non-zero, there will have to be an invertible intertwiner and exactly 1 in order to sort of not contradict the irreducibility of both of them. Okay. And if they're inequivalent, the same the same argument applies, right? So we have U, if they're inequivalent, then look at an intertwiner between the two things and look at the kernel, right? And the kernel will have a projection associated to it, which is in the endomorphism algebra of U, so it's either 0 or 1 up to a multiple. See it that way. Okay, so maybe I'll stop here, and when we resume after the break, I'll talk about unitarizability, which is a nice application of Haar measurement. Thanks.
Any questions before the break?
I think there are any examples about reducible representation.
Examples of irreducible representations? Yeah, my plan is to actually work through maybe the example of ON plus in some detail just to give a hint at how you would construct these things. Yeah, but as an exercise, you could look at the fundamental representation of ON plus, try and prove that's irreducible. Hint, the fundamental representation of ON is already irreducible. That's enough to get what you want. But SUQ2 may be a little bit more challenging. That representation is also irreducible.
So by saying that you are interested in finite dimensional representations, this is correct, but this is a very strong condition.
It is a very strong condition, yeah. So it turns out to really develop a duality theory and a Fourier transform, one needs to talk about also the regular representation like you do for ordinary compact groups. Mateusz will probably address that in more detail than I will, but the point is that's an infinite dimensional representation as you would expect. It's the translation action on L2, and that turns out is always decomposable, just like in the classical case as a direct sum of finite dimensional irreducible representations. So at the end of the day, finite dimensional representations are sufficient for all analysis, just like it is for compact groups by decomposition theory.
All right, then let's take a break and we reconvene quarter past the hour.
Something about the subconditions.
Yeah.
So this destroys unitarity.
Yes, in general. Yeah, so if you take a self-adjoint idempotence,
Right, okay.
yeah,
I mean,
it's natural, right? I mean, in the unitary case, you look at a.
All right, okay.
Yeah.
This is all right, okay.
Yeah. Yeah, so in general, it will destroy unitarity, but I mean, when you're working with unitary representations, it's natural to, you look at it, you can actually talk about invariant subspaces in a way. So you think of U as this tensor, right? B of H tensor C of G. So if you act by U on things of the form vector tensor identity, so something in H tensor 1, the unit of the algebra, this, you can think of it if you know about like, think of it as like a module action or something like this. You can talk about the image being invariant, so U acting on actually. Yeah, so you can talk about U, if I take a vector in H, okay, and I look at if this is always inside of, let's say, K is some subspace of H, right? And if it happens that this is is always contained in K tensor H, C of G. So in general, like this kind of thing will just end up in H tensor C of G, right? Because there's no, an invariant space would be something like this. So K is invariant at this kind of condition for all vectors in K. So in the unitary case, like what you usually do is you look at an invariant space. There will be a unique orthogonal projection onto K, and then what you would expect is true. The complement K perp, which is the image of 1 minus P, will be also an invariant subspace, and that partitions U as an honest direct sum of unitary subrepresentation.
So this means I can think about the representations also in terms of right C of G modules.
Exactly. Yeah, exactly. Right. These are like right C of G comodules because it's like somehow the tensor is kept there. Yeah. But that's exactly. So you can think of representations of comodules. So this is C of G has like a co-algebra structure because it's got this co-multiplication, and this formula really defines a co-module structure on H, and then there's natural notions of sub-modules, sub-co-modules, and stuff like that. It corresponds to exactly this notion of sub-representations.
Thank you.
Yep. Yes.
Sorry.
Sure, no problem.
Could you tell me, it was pretty clear to me when you were talking about the leg rotation
Yeah.
or
Sure.
it's erased.
Yeah. Right, so it's the definition?
I mean, when you write U tensor V is a representation.
Yeah.
So then.
So classically, right, this is a representation of G, and this is given by U, it's given by U of G tensor V of G. Which is, I mean, the way you should think about this, so this is in V of H U, V of H V. So what I'm doing is what you can really, the way you should think about this is like, we have U of G tensor U of V of H in general, where G and H are different, right? So this is just, this is like the honest tensor product of the two major C's, right? Where this is in C of G tensor V of H, this is in C of G tensor V of H U V, and I tensor them, and of course I'm maybe doing some shuffling of the legs, but this is the tensor product. But when I do the tensor product of a representation of a single group, I kind of want to match these two elements, right? And what that is, I mean, when you think about taking two variables and making them equal, this is doing multiplication in C of G. Yeah. So this is in C of G. This is the thing you can think of as something in V of HU tensor V of H V tensor C of G tensor C of G. The function of two variables associated to this. And now, if I take this and turn it into this, which is the tensor representation, what I'm doing is I'm multiplying these two, the components, the coordinates, I'm multiplying them, right? Because if you think about it, what is, if I have a function f tensor a function g, so this is f of g, f of s of t. And when I multiply them, what I'm doing is I'm doing f of t times g of t. So it's really just matching the variables. That's sort of what it is.
But this if C of G is, let's say, non-abelian.
Yeah.
Yeah, then U tensor V is not equivalent to V tensor
Yes.
V, right?
Yeah. That's a stark contrast.
Exactly, because the classical group.
Yes. Yeah. So those the tensor is like a symmetric operation. Yeah. You can up to a flip of the factors.
Yeah.
It's equivalent.
Does this have an application to braided?
Yes, it does. There are people who work in braided quantum groups. I am not so familiar with this area, but yeah, this is very much related because what happens often is that
My office is just
even in the quantum case, when the algebra is not commutative, U tensor V and V tensor U can be equivalent, but not in the obvious way, right? And the non-obvious way is coming from braiding. Yeah, yeah. So like it's a non-trivial, non-symmetric braid.
Thank you very much.
Yeah.
So in your definition of tensor product,
Yeah.
you have like U13, V23, but can you also commute them? Like V23, U13?
So
Classically, it's the same.
yes,
thing.
actually that was the same question.
Ah,
Yeah.
okay.
So yeah, I'll maybe make a comment since several
Okay.
people have asked that. Yeah, U tensor V is not V tensor U in general. Even up to equivalence is not the same.
Well, it's not exactly the same thing. So, like, so what I was could also define maybe do this.
Okay, so V13, V23,
Yeah.
and then here you're doing V23, U13. Yeah. So this would be the definition of V tensor U. So this will also be a tensor product representation, but it's not generally the same as this
Yeah,
one.
it's not the same. But it
Even for
also-
groups, it's not the same on the nose. It's the same up to an isomorphism.
But I mean, it should be the same on the nose because on the last leg you are commutative, so you can just. So,
Yes. Yes. But the point is, I mean, one is a representation on HU tensor HV. And this is a representation on HV tensor HU. I see what you're saying. Okay. I know you're doing something different. So this, yeah, you could. So what happens?
I think it's also.
So what happens is this will be a. I think this will be like an anti-representation or something.
Okay.
Yeah.
Because this bottom one should be like kind of equivalent to V tensor U through swapping V of HU and like HU and HV, right?
Right.
Because it's the same as V13 U23
Uh-huh.
composed with like the flip on the first swap.
But you would need something like braiding, no, to be able to relate them to each other. And do you always have braiding?
No,
This kind of
no,
thing?
you don't.
That's why I don't think.
Yeah, this is not going to work in general.
Braiding to relate them, you need something like braiding, and that's an
Yeah.
extra condition, I think. Otherwise, you cannot.
Yeah, that's very.
Well, so we do. Let's check one tensor delta of this thing V23 U13. Because it's a morphism, this will be one tensor delta V23. Okay, I'm going to put the numbering up top. And so you're going to have 3. So V is acting on the second and third leg, and then tensoring will produce an additional leg there, so it'll be 2, 4, 2, 3, 2, 3, V, 2, 4.
But can I make a comment on this? So because this is also about quantum information, it turns out that actually, from my point of view, these quantum groups have a very natural picture in terms of tensors.
Yeah.
Okay, so this would be like your space 0. Let's say this is a 0 and 1. This is a 0 and 1. These are your matrices. Okay, so this is like, if this is a 0, 0, you would say this is A. 0, 1, this is, what is it? What is your matrix? A, B? Like B. And then, okay, so you just draw it as such an object. And then you start asking, what are these objects? Like, how do I make a delta of something like this? Is actually equal to this. Okay, and you sum over that index. And your tensor product U times V is actually something like this. okay? Because
Yeah,
this is a tensor product space. And these are different ways, these are actually dual ways of taking a tensor product. But in many ways you can actually treat these and these as different, as equivalent degrees of freedom. So everything is symmetric. And
That's actually
I think this
Pontryagin duality.
and these and actually
Like, so rotation.
So the reason that I'm so interested in this is we developed this full framework for dealing with this for fusion categories.
Okay.
So this turns out to be the natural language for constructing representations of fusion categories, which
I think
generalize.
it just gives a representation.
My understanding is that it should be possible, and I don't think anybody has done that, to rephrase quantum groups in this language of fusion categories, such that these are effectively the Lie group.
You make a choice by putting one in front of the other.
And I think it's very. I think it's very useful to start drawing these. And this is, of course, my background is actually quantum information. That's why these are like quantum circuits. And this is exactly.
I don't expect them to be.
What's your name?
Frank. Oh, I'm here in Cambridge. Yeah, I forgot to. I forgot to. What do you call it? To subscribe myself to the conference.
They shut down the registration so early.
Well,
I can't believe anybody.
but my office is next door.
So you can just.
But I'm. Okay, but these things are
works. Yeah.
Well, indeed. So that's what, like this object is this one. And I think you want exactly what you want. That's why I say you need some braiding. No? You want to kind of swap these kind of two things. But for this, you need some notion of braiding. And from my experience, this is not obvious at all. This is an extra condition.
Yes, this would be 1, 3.
And one for, and then you can commute them.
Okay, yeah.
So it's funny. So basically, you make a choice by putting one for the other, but this one would not be the canonical choice.
No.
Yeah.
But sorry to go. So I'm really confused about your comment that every representation is at the end a direct sum of finite.
Yeah.
Because I know in physics is that typically there is not a single finite dimensional representation.
Right, yeah. So this is very specific to this case of a compact. Somehow the fact that
SU2, but take like SU with Q on the SE to the, let's say, E to the I theta.
Yeah.
Is that compact then?
No, this is the setting of
This is the
unitary
spectrum.
tensor
Exactly.
categories. Yeah.
Okay, I see.
Yeah. So this would be
Because there are no finite dimensional
that's
representations.
right, yeah. So
Unless Q is a root of unity. If theta is a root of unity, then it's fine. But otherwise, as far as I understand, there are no finite dimensional representations.
right.
So that's why I got confused that you said that.
That's right. Yes. That's right. Yeah. Somehow that setting is excluded from where we are.
Okay. But this is the case, of course, that appears in
I know.
physics.
Yeah. How about roots of unity? Do you like those?
But yes, these I'm happy. I'm happy with those.
No,
this is like this is the case that I really understand because for those ones I constructed NPOs of that kind.
Yeah.
That form representations of SU2 degree. So basically, I think the difference in this whole framework and the quantum group is that these legs, at the end, you have to do something with this. You have to take something like a trace over your. So put all these things actually, but these are these degrees of freedom in these finite dimensional Hilbert spaces, and we take the trace over this. So we identify these guys with each other, and then these are labeled by some group elements G. And although these objects are representations of SU2 level Q. The whole object as itself, you can multiply now.
So when you say representations of SU2 at level 2, are you talking about representations of the Q-deformed universal enveloping algebra?
And then if you take the matrix quantum group associated to these groups of unity, that's finite dimensional representation. You start multiplying something with a G, with an H, independent of the system size. This turns out to be equal to basically G times H. So that means that's why I was asking the other thing, that we construct representations of SU2, making use of SU2 level Q.
Classical SU2.
Yes, and it's not this is from the physics point of view, it's very surprising that things like the XXG chain actually has an SU2 symmetry. And the way we do this is by taking basically the quantum group thing, but doing one extra step, saying, okay, what do we do when we kind of take this tensor product of many things? You have to kind of get rid of your virtual degrees of freedom. These extra degrees of freedom that you have when you do representations. And then we just trace them out. And that is exactly the setting of these fusion categories. This is exactly somehow, then if you do it like this, the quantum groups are really the continuous analog of what you do in terms of fusion categories. And, but okay, that's what I'm really, it would be very interested in.
I actually plan to talk a little bit about last two lectures about tensor categories, how they fit in Waterloo distribution, but probably in a different sense than what you're thinking.
No,
Yeah.
but okay,
But it may be interesting.
But you're here probably in next a few weeks or.
I am, yeah.
I would love to understand this better, because I think there's really some. Hey, this is very relevant for.
Yeah, sure, we should.
For understanding entanglement, actually, in many point systems.
8 minutes. Okay, I gotta have a cup of tea.
So just like for, I mean, I guess find that.
Can we walk and talk? I just want to get a tea.
Absolutely, absolutely. Yeah. So like you mentioned, right, find a group sort of invertible or good in their group applications, it's the same. And yes, it's going to be nice to improve this here. But is there another reason that you chose to define them in general and not just unitary?
That's why I understood it's completely based on the fact that it's not actually this is just a rephrasing of the word that we did with continuous so the fusion category. Oh, that's my claim. My claim is that. That's what we
Mm. Oh, it was just that you want to talk about invariant subspaces, and that means like introducing how U acts on this Hilbert space, like co-module action. Yeah, I mean, there's some, it's a little bit of yes, exactly, exactly. I remember, you have to, somehow, one way to do it is to like actually turn a representation into an honest representation of the measure algebra. Do it that way, but it's a bit messy. What's that? Yeah, I'll just keep piling it onto you. All questions will be answered by Mateusz. Just what we planned, yeah.
break. So Mike will continue talking about representation theory, I assume.
Yes, thank you. Yeah, so in the first bit we saw how in a more or less straightforward way you can write down a lot of the notions that one has for representations for groups, for compact quantum groups, and it worked very seamlessly for the most part. And the next theorem I want to state and sort of give the idea of the proof of is actually unitarizability of finite dimensional representations. And this should be seen kind of as another reason why maybe the theory of compact quantum groups is a good one, in that it allows you to sort of generalize the theorems you have from classical compact groups to a much broader setting. Okay, and maybe if you've taken a course in representations of compact groups or finite groups, this might not come as such a big surprise, because when you do representation theory, at least the abstract part of the theory, Pt1 theory, orthogonality relations, complete reducibility, the analysis you're actually doing there is always linear algebra combined with analyzing functions on your group. So in a way, the whole theory of representations is already kind of quantized for our purposes. And this means that a lot of things you do for compact groups, you can see a path towards generalizing them to the quantum case. And here's an example, which is this unitarizability theorem. And so one of the things you learn early on in representation theory of finite or compact groups is that you might as well just look at unitary representations, because every non-unitary representation in the finite, let's say finite dimensional space, in fact, you can do infinite dimensional representations if you insist on uniformly bounded representations as well. But we won't worry about that for now. You can sort of average the inner product on your carrier space of your representation to make your representation into an equivalent unitary one. Okay, so let me just make sure my notation. Yeah. Okay. Yeah. So let U be a representation, finite dimensional as always. Okay. Then U is equivalent to a unitary representation. Okay. All right. So the idea, and this is a very nice application of the fact that we have an analog of a translation invariant power measure. Okay. So I have this U, and I know it's invertible, but I don't know that its inverse is equal to U star. That's what it means to be unitary. Okay, so I'm going to define an operator Q, which is identity tensor of the Haar measure of U star U. All right, so this is an operator in V of H, U. Okay. Q is positive semi-definite, because what I'm doing is I'm taking U star U, which is positive operator in this tensor product, and then I'm slicing it by a positive linear functional, and a little bit of operator algebra analysis tells you that slicing a positive thing by a positive functional, you'll stay positive, and it's invertible. Okay, and the reason it's invertible is because, well, U is invertible, so U star U will be invertible. Which means that U star U as an operator with the order on a C star algebra, U star U will be strictly bigger than 0, and therefore when I slice it still will be strictly bigger than 0. So you can check these things and you get an invertible positive operator. And then I'm going to define my new representation V, to be the square root of Q U square root of Q times U times the square root of Q inverse. Okay. And so this new representation is on the same space H, and it's now unitary. Okay. So why is it unitary? So the claim is that V is unitary. So V is unitary. Well, first of all, V is a representation. If I take any representation and I conjugate it by an invertible operator, I get another representation, which is automatically equivalent to V, right? So Q will automatically, and its square root will be automatic. The square root will be an intertwiner between U and V. Just if you look at the definition of intertwiners, that will be the case. And V is unitary, so maybe we can check one side of that question, V star V. Right, V being unitary, I want to check that this is the identity. Okay, and let's check what this is. So I just write it all out, Q to the 1/2. Q to the minus 1/2. U star, Q to the 1/2, and then I have another Q to the 1/2, U, Q to the 1/2, minus 1/2. Yeah. All right, so this is Q to the minus 1/2 U star. And then I have Q in the middle. Q, by definition, is identity tensor H of U star U. And then I will have U, and then Q to the minus 1/2. Right. And now, the trick is I somehow want to use translation invariance of the Haar state. All right, so what I'll do is I'll sort of swap the order of conjugation by U with the application of H. Okay, so the way I can do that is I can write it this way. So I have identity tensor H tensor identity. All right, and then I'm going to have 4 copies of U, 2 of them with stars. There'll be leg numbering now attached to them. Okay. So what leg numbering do we need? So this thing is being put now as a thing on a triple tensor product. So the U star U is acting on the first and second leg. And then this U will be acting on the first and the third leg. So that's what you get. Okay. All right. Now, what is this whole thing here? This is U12, U13 times its adjoint. Right, that's what this is here. All right, but then if you look at our definition of a representation, U12, U13 is actually identity tensor delta U. Okay? So this is identity tensor delta U. Delta is a star homomorphism, so this will be the adjoint of identity tensor delta U. Again, star homomorphism, I can find everything to give me that this is identity tensor delta of U star U. So all of these 3 things are the same thing that I'm applying H to. All right. And so at the end, I get Q to the minus 1/2. And then I have, well, let's see. I have identity tensor delta. And here I have H tensor identity applied to delta, which is actually the same as just applying H and not doing delta. Okay? So after a couple seconds, you see that this is just going to be identity tensor H of U star U times Q to the minus 1/2. And this is Q, right? So it's Q. And so altogether, everything cancels and you get the identity. So V is an isometry. you can basically do the other calculation and sort of same sort of algebra works out. So same for EV star. Okay, so you automatically get a unitary on this.
Anything about y is invertible?
I sort of said verbally, so U star U, so U is invertible. So U star U will be a positive invertible element. And so which means, if you think about positive operators in C star algebras, that means there's some epsilon bigger than 0 such that U star U is bigger than epsilon times 1. When I apply a state to that equation, the inequality will be preserved, which will tell me that Q is bigger than epsilon times 1. Okay, so this is nice, and if you think about the classical proof, it's exactly the same, just written in a way that we can make sense of when we don't actually have points, okay? What you do is, right, you take your arbitrary inner product on your Hilbert space, and you define a new inner product on your Hilbert space by averaging your original inner product against the representation, right? So you take an inner product of U, or psi tensor, psi and eta, and you write pi of G psi, inner product pi of G eta, and then you integrate that over the group, and that new inner product happens to be one which makes your representation unitary. And if you write that another way, so you bring the pi on the right side of the inner product over, you get pi star G pi of G. And that's exactly the U star U here that you have here. Okay? So the averaging of the inner product is changing the inner product. And when you change inner products, that's really implemented by some positive, strictly positive operator. And that's where this Q is coming from. Okay? So it really is paralleling what you get in classical case. So this is, I guess, the theorem of Wasilewski. Okay. So maybe just a remark. You can do more general averaging techniques, just like you do in group theory, right? So if I have T, an operator on the Hilbert spaces between two representations, HU, HV, okay? I can define E of T to be the average of V inverse T tensor 1 U against the Haar measure, okay? So what I do is I take an operator, right? Classically, you take an operator and you right compose with the one representation and left compose with the inverse of the other representation. And then you average over the group this conjugation type operation. And the point is this thing is now turned into a morphism from U to V. Okay? And in fact, E is an idempotent map from V of HU, V of HV onto the morphisms from U to V. Okay, E squared Z. Okay, and in fact, it's it's a bimodule morphism. If you think of these as left end U, right, or rather right end U, left end V bimodules. Okay. So this kind of thing you use all the time in representation theory, right? So if I want to find all the intertwiners between a representation, formally I can compute them all, or I can produce them from all linear maps by averaging. Okay? So again, these kinds of techniques are really, one might say representation theory is pointless because you actually never need any points in your space to do representation theory. You just, everything is done at the level of function algebras and matrix algebra. Okay? And maybe I can also mention, one can talk about complete reducibility of finite dimensional representations. So it turns out you can also do this for infinite dimensional representations. The proof's a little bit more involved, but not too much more involved. So if U is a representation, then U is equivalent to a direct sum of irreducible subrepresentations. Okay. And again, maybe it's worthwhile just seeing how you do this without loss of generality. Well, what do? I can assume U is unitary because I can always unitarize U. Right? So then I can assume that the endomorphism algebra of U is a finite dimensional C-star algebra. Okay? And then what I can do is I can take P1 up to Pn, a maximal family of minimal central projections. So again, a finite dimensional C-star algebra is a direct sum of matrix algebras, Mni. Okay? And the PIs are just the identity operator in the Ni block. Okay? And so the endomorphisms of U are going to be identified with this multi-matrix algebra. The minimal central projections are these identity matrices in these subblocks in the decomposition. And then I write U as a direct sum, identified naturally from 1 to n, of some representations Ui, where Ui is just the compression of U by Pi. That's the proof.
Just to clarify it, so that when you say minimal central projection here, you mean central projections that are minimal among central projections?
Yes, yes, yes. Okay. Right. Good. So yeah, this is nice. Maybe continue our list of representation constructions. One might be worthwhile just mentioning another construction, which is this contragradient. So this you should think of as like the notion of a dual representation. Okay, and I'll maybe just be short about this and just say, okay, let's think about a unitary representation since we can always unitarize things. Okay, so if U is a unitary representation, although this is not strictly necessary, okay, then as we saw before, UC, so if I think of U as a matrix concretely, okay, UC is just this matrix Uij, and now I add stars on every entry.
You got ahead of yourself at the start of the second one.
Oh yeah, so I did, yes, thank you. Yeah. So UC, this is like the entry-wise adjoint, okay? It's sort of natural to think of this, if you think about unitary representations, when you place bars over all the entries, the natural, you get a unitary representation again for a group, and this is sort of acting on the conjugate space. So this is sort of like the conjugate or dual representation. And you can do this more generally using transposes for non-unitary representations. But you know, this is a thing you can write down. One easy calculation is that if I do identity tensor delta, the fact that delta is a star map and a homomorphism and all that stuff tells us that this is going to have this relation that a representation should satisfy. But is UC invertible? Or better, is it unitary? And this is a non-trivial question. So if you just throw out, you know, to me, a unitary matrix with operator entries, and I take its entry-wise adjoint, it, generally speaking, is not going to be a unitary, okay? Unless the entries commute, then you're guaranteed for this to happen, okay? So this is a non-trivial question when the entries are non-commuting. And tomorrow in the tutorial, I think it'll be a good opportunity for us to actually give examples where this sort of unitarity of this sort of UC in the case of like outside of compact quantum groups happens. And it's very much related to the quantum information talk this morning and the non-complete positivity of the transpose map. So it'll tie in nicely to that. So we'll talk about that maybe in the tutorial tomorrow. But this is a natural question, and okay, it's non-trivial. That actually the answer is yes. Okay, so the sort of co-multiplicativity condition of UC works very easily. Unitarity or invertibility, while unitarity is not always true, but invertibility is true. Okay, so UC is a representation, and this is the contragradient representation. Okay, and maybe a calculation one could try and do is to look at the fundamental representation of SUQ2. Okay, this is this representation of SUQ2. Okay, UC is not unitary. Okay, so the contragradient is not unitary. So this is something that's very different from the classical case. You can do a sort of analog of a dual representation, but you get a non-unitary representation in general. All of the other examples were constructed so that UC was actually equal to U, or guaranteed to be unitary at least, like UN plus, ON plus, SN plus, and so on. So this is this contragradient representation. It's not unitary, but we've just shown that it's similar to a unitary, okay? So unitarize UC, okay? In the same way we did, so you take this Q associated to UC, and we're gonna get U bar, which is Q to the 1/2 U to the negative 1/2. This is now a unitary representation interpreted on the dual space H bar. Okay, and this is what's called the conjugate representation.
So what is Q in this case? What you do?
Yeah, this is SUQ2. Yeah, and Q is, as mentioned last time, between -1 and 1, not equal to 0. Sorry? Q, well, it's this, right, from the theorem.
Yeah, but I will write it down explicitly for this.
For this, the capital Q, you can, but I don't know it off by heart.
But the answer is yes.
Yes, you can, yes, yeah. Exercise for tomorrow, actually, great exercise. Yeah. Mateusz will cover it tomorrow. Okay, yeah, so this is contragradient representation.
So if I take the tensor product U with its contragradient or conjugate, does it contain the identity, the trivial representation?
Yes. So U tensor U bar will always contain the trivial representation. Same for the contragradient. In fact, a nice exercise, everything's an exercise, is take an orthonormal basis for your Hilbert space H and a unitary representation, and look at the the Bell state on H tensor H bar. So that will be sum over I, EI tensor EI bar. That will be always a fixed vector of U tensor U contragradient. And if U is irreducible, it's actually up to a scale factor, the unique fixed vector. Okay. All right. So maybe in the last like 18 minutes, I guess, let me kind of end by kind of talking a little bit about how the Hopf algebra structure comes back into this when you think about representations. So when Mateusz was motivating quantum groups, one was naturally led to the axioms of Hopf algebras, okay? And then immediately when you started looking at examples, you come across, well, in our lectures, just one, SUQ2, but many examples one encounters in practice are the C-star algebra formulation is not a Hopf-star algebra, okay? It's not even a Hopf, you know, you could try and define a C-star analog of this, but things break down because things like antipodes and stuff become unbounded. And you can rectify this once you sort of shrink down your attention from all of C of G to a smaller subalgebra, which happens to be dense, okay? So here's the idea. I'm going to let ear of G be the collection of equivalence classes of ear-reps, unitary, without lots of generality, of, okay, and for I, one of these equivalence classes, I'm going to fix a representative. U pi, which I will also sort of write canonically, or not canonically, with respect to some basis. Okay. So I and J will be running for 1 up to d pi, where d pi is the dimension of the representation. D of H, dimension of H pi. And what I'm going to do is I'm going to define O of G. Also, this is often called all of G. Okay. And I'm going to define it to be the linear span of all these coefficients ui, j, pi. So I just have a linear space. And now if you think about direct sums, tensor products, and stuff like that, it's not too hard to convince yourself that this is also equal to the collection of all following things, and I'll explain my notation in a second. Omega C psi tensor eta identity of U, where U is a finite dimensional representation, possibly unitary, not unitary, I don't really care. Let's say in some B of H, tensor C of G, and psi, eta are vectors in H. And this omega C eta is the functional, which is the norm, the usual thing where you take T inner product T eta. Linear inner product on the right side, let's say. So basically, I mean, what we're doing here is, you know, when you have a representation of a group, you look at the function pi of G eta inner product C. This is what's usually called a coefficient function of a representation. And that's what this is in the case of, the notation we have for forming. Okay? And if you think about it, I mean, a scale on this term I can just push down to the terms C and eta. So this is closed under scaling. Sums it's closed under because I can take direct sums of finite dimensional representations. I can also decompose something like this into a linear combination of things like this. Okay. So these are one and the same thing. So the space of coefficients of finite dimensional representations is a linear space. It's an algebra too. Right? So I can take the product of this with another thing, and I can realize that as the coefficient function of the corresponding tensor product representation. Okay? So O of G, it's an algebra. It's actually, it's an involutive algebra coming from the one that it's sitting inside of, C of G. And why is that? Well, again, just think about this. If I take the star of something like this, I can interpret that as a matrix element of the contragradient of pi. Okay. And I know I can unitorize a contragradient to assume that it's a coefficient of a unitary representation and break it up into a sum of these types of things. Okay. So this O of G is a subalgebra of C of G. Okay, star subalgebra. Non-trivial fact, it's actually dense. Okay. To prove this density condition requires a bit more work. One needs to show that anything in C of G can be approximated by coefficients of finite dimensional representations. And that requires actually one to look at coefficients of the left regular representation, which is an infinite dimensional one. And Mateusz will clarify all matters on that in his lecture. Okay, but even more is true. O of G is a Hopf star algebra.
But from matrix compact.
Oh, yes.
It's easy, right?
Yeah, that's a great comment. Yeah, so Matt's comment was that for matrix compact quantum groups, the density of O of G inside of C of G is automatically true because the star algebra generated by U is contained in O of G, and C of G is a closure of that star algebra. So it's automatically dense. So like in practical situations, the density is, yeah.
To continue, even then, okay, because then O of G is actually this algebra.
Yes,
you
it is.
just mentioned,
It
but
is.
that's already treated, right?
O of G is this algebra. Yeah, you need to see that.
So this will be covered by
Yeah, that's Mateusz's. He asked to do that himself. Okay, I want to just explain that. So basically, if you sort of look at a dense subalgebra, which in essence, because it's dense, sort of still carries all the information of your original C-star algebra, you can actually define the structure maps of a Hopf algebra. Okay, and there, working on coefficients of representations, you have natural candidates of these things. So I want to define a map from O of G to itself, linear. It'll turn out to be an anti-homomorphism of the algebra, but that's not so important for us now. There'll be a co-unit, and there will be a co-multiplication. And this is the obvious one. It's the restriction of the co-multiplication from the C-star algebra to O of G. But for Hopf algebra, we require that the co-multiplication is really an algebraic thing, right? We want it to land in the algebraic tensor product, not some completion or anything like that. But again, that's clear, right? Because the co-multiplication on a representation, you look at a Uij, when you apply delta to it, you only get a finite sum of terms, Uik tensor Ukj. Okay? So we have this natural map. It's co-associative by the fact that the ambient one we started with was. This is a linear functional, and this. So what is epsilon? Well, epsilon again is like evaluating functions at the identity. If I do it to a representation, what am I doing? So I'll define epsilon by how it acts on the entire representation by amplification. So if I have a finite dimensional, let's say unitary representation or non-unitary, doesn't really matter, identity tensor epsilon, this should be basically evaluating u at the identity. What does that mean? Well, a representation evaluated at the identity is always the identity operator. So I'm going to demand epsilon to be defined this way. And here, I'm going to ask that S S is the inversion map on a representation, right? So if I, again, think about how we thought the antipode should behave, S of a function at a point G is F at G inverse. So applying S to a matrix valued function, which is a representation, well, U of G inverse is U of G inverted. So we can sort of, these are sort of the proposed maps, and the conditions for a Hopf algebra so this is sort of the candidate definition that one would take. Matches the classical case. Are they well defined? Well, one needs maybe a little bit more like the Schur orthogonality relations to know that you have a basis of irreducible representations. Maybe it's not. Well, whether these maps are well defined at the moment, I think some work may be required, but it's not overly demanding, I guess. But we'll leave that for now. Okay, so what do we require? We require that multiplication in the algebra, so M is the multiplication map on O of G. This should be the same as M S tensor identity delta is the same as M identity tensor S delta. And this should be the same as applying the co-unit. And similarly, slicing the coproduct by the co-unit is the same as just applying the identity map. Okay. So formally, I mean, like, why would something like this be true? Okay. So let's check maybe just the first condition. Okay. So if I do M of S tensor identity delta, what does that look like? Well, let's check it on a representation. Okay, so I do identity tensor M S tensor 1 delta. And now I apply it to a representation U. Okay, so if I apply delta to U, I look at my formula for the co-multiplication on a representation. We're going to get identity tensor multiplication of S tensor identity of U1 to U13. Okay. S is applied to U12, so I can remove this S and apply it here. That turns U12 into an inverse. And then I multiply on the second and third leg the C of G factor in them. Okay? So what does that give me? This is just going to give me U. So these two legs are multiplied, and I'm going to just end up with U inverse U. And this is equal to the identity matrix, which by definition of epsilon is identity tensor epsilon of U. Okay? So this map and this map agree when I slice on all the U's. My space is basically spanned by such coefficients of U, and so these maps have. Okay? And you can do all these calculations in a similar fashion. So you get a Hopf algebra from this. All right. So I will maybe just end in the last 5 minutes by talking about, just mentioning at least, this notion of universal and reduced version of G. Okay. All right, so again, we start with C of G, right, our compact quantum group, and sitting inside of it is some algebraic object O of G. And this is an actual, honest star algebra where, by Hopf star algebra, by the way, I should say, that means that delta is a star homomorphism and epsilon is a star map. It's sort of automatic, actually. Okay. So I have this object here, yes? Oh, yes, yes. So I have this thing here, all right? And now what I could do is I could sort of look at this star algebra and sort of try and complete it back to a C star algebra in a few different ways. So I could define a universal completion, which is like the C star enveloping C star algebra. So if I have a star algebra, I can try and ask, is there some universal C star algebra that this thing sits inside densely? And because O of G is spanned by coefficients of unitary representations, it turns out this universal object can be made to exist. Okay? And actually, it's not too hard using kind of universal constructions. The co-multiplication on O of G extends to a co-multiplication delta U from the universal C star algebra Cu of G onto Cu of G tensor C. Okay? So what we get is somehow sitting above some universal C star algebra, our original one. Okay? And another thing I could do is define a reduced version, CR of G, which is going to be, thankfully we learned about the GNS representation this morning. I take the GNS representation associated with the Haar state, and I look at the image of that sitting inside of the bounded operators on the GNS Hilbert space of the Haar state, which is usually written V of L2 of G. CG, yeah. And let me just end by saying CR of G also, the coproduct kind of extends from the Hopf algebra or the full C star algebra to the reduced, okay? So delta U, delta, these drop to a co-multiplication delta R on CR of G. Okay? And in fact, let me just end by saying O of G, the Haar state, if I restrict it here, is faithful. The Haar state is always faithful on the Hopf star algebra. So the Hopf algebra that we started is sitting inside of the reduced algebra as well, densely. Okay. So oh yes, yeah. So all this is to say is that we started with some arbitrary C of G compact quantum group given by a C star algebra realization. Through representation theory, you boil it down to some sort of purely algebraic object, which is this space of coefficients of finite dimensional representations. And the data of the original analytic object is somehow remembered by doing C star completions. But the thing is, you can complete in different ways. You can take a universal completion, you can take a very concrete one by doing the GNS with respect to the Haar state. And this is very much an analogy with what you get for group C-star algebras, right? You start with a group. The algebraic Hopf algebra associated to a discrete group is the group algebra, and the universal one is the universal C-star algebra, and the reduced one is the reduced C-star algebra of the group. And so these kind of things happen for quantum groups as well. And I'll stop there. Thank you.
Any quick questions before we? In the normal representation theory, the most important thing are the characters. You didn't talk about this at all.
No, I didn't. I could talk about them if you want. Or Mateusz will talk about them. But actually, in the tutorial, it would be maybe on Friday. I could talk about characters in the afternoon.
How would you define them?
Yeah, you can. I mean, it's the same idea. You take one of these matrices U and you look at the trace.
That's it.
Yeah, and sum the diagonal entries, and all of the lovely formulas for character theory work. Yeah.
For matrix the universal algebra right here focus with the torsional.
So maybe, I'm not sure if I'm answering your question, but what I'm guessing you're asking is like in the examples like Sn plus.
Yeah.
So the way those were defined were as universal C-star algebras, right? So the object that was actually being constructed in practice is always Cu of G in all of the examples actually. And somewhere sitting down below is a Cr of G version as well. And possibly a continuum of things in between. But in a sense, they're all sort of completions of the single O of G algebraic object.
Maybe these two more, and then probably move to the next.
Yeah.
If you try to extend the antipode or the co-unit, you run into the same trouble as before, I guess. Or...
Yes, you do. So yeah, I mean, these are obviously well defined on this level. Yeah, the point is that, for example, if you look at the left regular representation, this will decompose into a direct sum of irreducible U's. And if you apply, sort of extend the formula there, you'll get sort of blow up in the sort of norms of these things in the limit. So yeah, it won't work. Oh no, that's not true for the regular representation. No, it's not true. Yeah, it's just it's still again U star for coefficients, but yeah.
I was going to say, I mean, co-units of these things.
Ah, yes, okay, yeah. Yeah, different issues, yeah. So co-unit always is well defined on the universal C-star algebra. Not always. Yeah, the Haar state is always faithful on the reduced, but not on universal. That's also kind of maybe a little mysterious, and it's something I'd be happy to talk about in concrete examples on one of the tutorials.
What happens if we take the conjugate rep of the conjugate rep?
Good question. Yeah, so we take the conjugate of the conjugate. It's naturally isomorphic.
But not equal.
Not equal in general.
Convert. Is there a way to make this iteration converge in any sense?
Don't know.
Well, no, but what do you mean by taking the conjugate? I mean, the way you defined it, I mean, obviously, if you see, then you do it twice.
Oh, yes.
Contragradient
Yes.
twice?
Contragradient twice just gives you the same thing.
No, but this
You
is
take the contragradient of
No. I mean, yeah, formally it's, you take U inverse and then you do the transpose on one leg. So doing it twice, even if you start with something unitary, it won't bring you back. You'll get something that's non-unitary but equivalent.